on the reflections handout that you were given, you were first asked to sketch a graph of y equals the square root of x, is that right? On that first page. And this is what it looks like. It's like half a parabola on its side, right? That's y equals the square root of x. And then the second one, you were going to do y equals negative the square root of x. And how does that compare to the square root of x? It's reflected. And we say that it's reflected in the x-axis. It's a vertical reflection in the x-axis. So it reflects vertically because it switches up and down, but the line of reflection is the x-axis. So when we go to fill in this information, the graph of y equals negative f of x. So you take any function and put a negative in front of it. It's congruent to the graph of y equals f of x. So it doesn't change size or change shape. But it is, so here we have by a reflection, a vertical reflection in the x-axis. Invariant points are points that don't change when you transform a graph. So for this reflection, if you look at the original one and the reflected one, there's only one point that stayed the same. Which point is it? It's at the origin, right? 0, 0. But we need to think it's not always going to be the point at 0, 0. When we reflect something vertically, what points are not going to change? Just in general. The x-intercepts are the invariant points. So invariant points occur on the x-axis. Then we need to write a mapping rule. X, Y maps to if invariant points occur on the x-axis, that's because the x values are not changing. So for the mapping rule, x, y maps to x. X is not going to change, but what happens to the y values? They become opposite sign, right? So negative y. If they're already positive, they start out positive, they all switch to negative. If they start out negative, they switch to positive. So x and negative y is the mapping rule for a vertical reflection in the x-axis. And that happens when you put a negative in front of an entire function. Here's the next graphs that you were doing. Again, starting with y equals the square root of x. But then the second one asks you to do y equals the square root of negative x. And that's different from the one we did on the previous slide, because there you had negative square root of x. Here you have the square root of negative x. So the negative is just on the x value, not in front of the whole function. And what do you see that happens there? What kind of transformation? A horizontal reflection in the y-axis. So that's what we'll fill in that blank. So now if we're reflecting in the y-axis, where do the invariant points occur? On the y-axis. Yeah, the y-intercepts. So it's still looks the same in terms of here it's the origin, but it's the points on the y-axis that are not changing. So invariant points occur on the y-axis. And for the mapping rule, x, y maps to negative x and y. It's the x values that switch signs, the y values stay the same. Here's a function f of x, and we're asked to sketch y equals negative f of x. And I just want to show you how you can use a mapping rule to do that. You don't necessarily need to use a mapping rule. When there's only one transformation, it's pretty easy to draw. But if we were going to use a mapping rule for this, what would the mapping rule be? x, negative y, that's right. So what I'm going to do for this is choose some points on the function, and I'm going to choose those points where it's switching direction from increasing to decreasing, and the endpoints. And I'm just going to make a list of ordered pairs here. So I have 1, 2, 3, 4. Negative 5 and 2 is 1 point. Negative 3 and 0. 0 and 3. I'm just picking these points off of the original function that we're given. 3, negative 3. And then 5, negative 2. Those are kind of the critical points on that function where it's switching direction. And it's all straight lines in between. So I know if I transform those points, I can just draw straight lines in between. So now I'm going to use the mapping rule to write the new points. So this point 5, negative 2 maps to, or sorry, negative 5, 2 maps to negative 5, negative 2, right. So the x value stays the same, the y value switches signs. So this one is going to be negative 3, 0. That's an invariant point. It didn't change at all. This one's going to go 0, negative 3. What happens to this point? It's at 3, negative 3. It goes to 3 and positive 3. So negative here doesn't mean make it negative. It means switch the sign or multiply it by negative 1. And then this last one becomes 5 and 2. So now if I plot those points, the transform points, I'll get the new function. So I'm going to go negative 5, negative 2, negative 3, 0. Like I said, that's an invariant point. 0, negative 3. And then 3, 3, and 5, 2. I've plotted all those points, and then I'm just going to, because the original points went left to right, I'm going to join them from left to right. Sorry, it's hard to draw straight lines on here, and a ruler just doesn't work. But that's what it should look like. So the whole thing is reflected. How many invariant points are there? So there's this one, right, that we had listed, the negative 3, 0. Where's the other one? It's right there, right? 3 over. So for this one, what would the mapping rule be? It's asking us to take this function f of x and sketch y equals f of negative x. xy maps to negative x, y. The original points are the same as they were on the previous graph, but now we're switching the x value instead of the y. So the new points will be 5, 2, 3, 0, 0, 3. There's the invariant point. This one didn't change. Negative 3, negative 3, and negative 5, negative 2. I'll plot those points. 5, 2. 1, 2, 3, 0. I'm going to join those right away. Sometimes it's easier if you join them right away rather than plot all the points and then try to join them. 0, 3. So that's that invariant point we talked about. -3, -3. So down there. And -5, -2. That's the horizontal reflection in the y-axis.